Yes, I met him a couple months ago. He gave me a call and said he had a new theory, and I get a lot of calls like that. And but this person seemed like he really knew what he was talking about, and we worked for about 2 months to get together. And he came by our house and demonstrated what you're going to see here. He gave me about maybe 5 or 6 hours of demonstrations on his electromagnetic spherical theory. People say, well, what is electromagnetism? How does it propagate? There's a lot of known laws as to what happens. We can engineer equipment to make it work, and the theory you're going to see doesn't really change that, but it does help understand in a very common sense way the actual propagation effects of the energy. So it really is a good pleasure to introduce a person who's become a very good friend, Larry Spring. And I would also like to add he's being assisted by his wonderful wife, Louise.
I think the first way to get started with this was to kind of give you a little background of my experience with electromagnetic energy. I was in the Air Force, the Army Air Corps at the time, because it wasn't the Air Force at that time. And after I got out of the service, I was deeply interested in radio reception and into television reception, not as the set itself, but as the energy came to the antennas and how to get better reception. The reception was very weak out in the area where I was. It's at Fort Bragg, California, but I was southeast of Fort Bragg, out in the mountains there, and about 1,000 feet high. And we were able to reach San Francisco, channel 4 and 5, but it was a fringe area, a real fringe area. So we had to do everything we could to get as much signal as possible. And this is where my experimentation come in and got me into a lot of, into the television business and then into other things. But basically, I had no formal education on electronics. And to some extent, that was helpful to me because I had no preconceived ideas of what things should be like. I wasn't hammered in any shape. I just let the energy tell me what it was trying to tell me, and I hoped that I was able to recognize and properly analyze what I was seeing happening. So back in 1954, well actually it's 53 I started working with television, and 54 I got a field strength meter, it was a radion field strength meter. Now I don't know if you folks know what a field strength meter is, but it's like a little needle you see on your receivers that go back and forth. The more signal you get in, the higher it goes. And it's portable. This was a portable thing. And I used an antenna like this, not anything very fancy, but it was a 2/4 wavelength antennas, which is actually a dipole. It makes a half wavelength across it. And it was a very efficient little way of experimenting with signal. And so I was doing some work with adding antennas together, and I come upon something that I realized after I'd done it, that I had measured the speed of light. And hey, that's kind of neat, you know, be able to measure the speed of light. What I did was I didn't actually measure the speed of light from a known distance. I measured one wavelength, or I could easily measure 2 wavelengths. But the thing is that when signal is sent out, like I was using 4 and 5 out of San Francisco, but I'm more familiar with channel 3 out of Eureka, so I'll use that as a measurement. And if it's sent out between 60 and 66 million cycles a second, the video is sent out at 61.25, but I'll use 60 because I won't even talk in approximations. I don't want to get into a lot of little detailed figures. So anyway, I set these 2 antennas up, one right opposite the other, and running a ribbon lead. Now this is a ribbon lead here. Some people aren't familiar with ribbon leads and ladder lines, but this is a flat ribbon lead, and it is a good lead. It has 2 wires in it, one wire going to one side of the antenna, one going to the other, and this goes into your television set. Well, I was running this into a field strength meter, and I had a long piece of this here. In fact, I took 2 of them because I had 2 antennas. I'll set this up here so that this isn't really the way an antenna goes together. If I was to jam them together like this, it was just short out in the middle. So you have to think of this as an insulator. We're going to have to do a lot of thinking. I didn't really come prepared to give a real scientific demonstration, but I can give you what the energy was telling me, and you can make up your own opinion of what you think. So this is an insulator here. This is a ribbon lead going down to a field strength meter. This is another antenna, and a ribbon lead going to the field strength meter. And we'll say the signal is coming from over in that pyramid hanging on the wall there. That could be way out there 100 miles. And I had the two antennas right opposite each other like this, and when the signal hit on both antennas equally and went down the same lead length, the same lead line, it would add together, and I'd get about a 30% gain of signal on the field strength meter. So then I started walking ahead. I'll come up here to do that, so I don't put somebody's eyes out. And I walked ahead, and I got to a point, and the meter kept dropping down, the needle kept going down, so I got to 0. Now, that's kind of interesting. I just was getting them out of phase, and it was feeding them in against each other out of phase, so it was canceling each other out.
You have to come back into the light.
Yeah, I think I better work. I'll work around the podium here. So I come out to the half wavelength point, and I got a 0 reading, a null. Then I went ahead further, and I got another maximum reading. And so I just measured the distance between maximum and maximum, and I got one wavelength. Then all I had to do was multiply it by 60 megacycles, 60 million cycles a second. I call them cycles at that time. They call them megahertz now because Heinrich Hertz is supposed to have first recognized the alternating current. And so all I had to do was measure this one wavelength, and I could measure speed of light. Now, in accurately measuring, I think you'd come down within 2% of the speed of light, probably as close as anybody else could measure it. But the interesting thing about this was that as I went back to the null point here, halfway back, I switched the antenna around like this, and then it would be the same as changing the leads on the field strength meter. But as I switched it around like this, I got the maximum here where the null was, and then I went back here, and I got the null where the maximum was. So I'll get null to null, then the null would be over the maximum. Now null is much easier to work with because you get two equal signals going into a field strength meter, and that needle would drop right down to 0. While if you get the maximum, I only got about 30% gain, and it's a lot harder to read it. So I get a very accurate reading on the nulls. So I used the nulls for all my measurements after that. I'm keeping my hat on for one reason. It gives me a little chance to see the audience. I didn't want the lights to be in my eyes too much. Anyway, that was in 1954. And I put this down in my notes, which I always do. I always make notes of everything I do so I don't have to go back through the experimentation again. And I think it's a very wise thing for anybody that's doing experimentation to do that instead of trying to remember it. So anyway, we've measured one wavelength and we multiplied by the frequency. We come out with 186,000 miles a second. Now that's a figure you could write 300,000 kilometers a second, or with a 3 million, no, it'd be more than that, meters a second. Anyway, I used to work in feet and inches because I'm a little older than some of you people, and we weren't working the metric system at that time particularly. And anyway, when I measured the speed of light, I thought, that's a real neat thing to be able to do. But I also then wondered how fast it propagated on the lead line. So I took these two antennas right opposite each other again, like this. Let's stay up here, watch it. Right opposite each other, and I was using the null point now, and I started adding pieces of lead. I had them both hooked to the field strength meters down on the ground there. I was out in the field doing this, out in the clear of everything. I don't think you could possibly do this kind of measurement in towns or close to stations. It's had to be in a fringe area in a very weak signal condition. Anyway, I started adding pieces of lead because I didn't know what was going to happen. So I just added like 2 feet of lead, 2 feet at a time, till I went from the null through the maximum and back to the null. Then I measured the lead line to see what the propagation on the lead line was. and I found that the propagation on lead line, ribbon lead, was about 75% of the speed of light. I checked ladder line. I don't know if any of you people are familiar with ladder line, but it's a twin wire, comes down a whole bunch of little spacers across it. And that was about 90% of the speed of light. Since then, I've worked with coax some, and it appears to be about 66% the speed of light. But that's pretty fast. Speed of light. Anybody really conceive what the speed of light is? I got a little story to tell. Sometimes I kind of hesitate to tell it, but it might be worthwhile because you get the point across better. There was a party told me this in a little different way, but I kind of dressed it up a bit. I guess I did. Anyway, there was an explorer, and he was going up a steep mountain. And boy, he just worked and worked, and finally got to the top of this mountain, and he was standing up there, starting to congratulate himself for making it up there safely. And he looked over, and here was this big grizzly bear. And this big grizzly bear was up on his hind legs, and he was going to come right at him and tear him up. So he, modern explorer, he whipped out a rifle that he had, and was able to shoot a bullet at the speed of light. And so he got off one shot at that grizzly bear, hit the target, and that bullet at the speed of light went around the Earth, and it could go 7 times around the Earth in a second. So by the time that grizzly bear collapsed to the ground, he had 7 holes in him. And that's clear around the Earth, and I thought across the oceans and across the continents. It's like 7 holes in 1 second. That gives you a little better description of 300,000 is 10 to the 6th power, whatever it is. Anyway, I guess it's to the 5th. Anyway, that story goes on. If there are any ecologists, a lot of ecologists out here, I presume some of you are. That story, as I recognize it, goes on a little farther. Nobody has invented a bullet to go at the speed of light, or a rifle that could send a bullet, because that's mass. It takes energy to move it that fast. I'm not saying it isn't possible, but I'm saying that we don't have them yet today. Now, you can send a beam of light, a laser or something at that speed, but the mass hasn't been able to move that fast. But anyway, I was going to say that lost my train of thought here, and I guess you recognize that. I'm not much of a speaker, really. I do a lot of thinking, and this is the first, actually, this is something unusual. This is the first time I'm giving this type of demonstration to an audience of this size. The other time we demonstrated was at the Exploratorium in San Francisco to about 15 people of the Exploratorium to see if they would want to use some of these things in their demonstrations. But anyway, going back to the bullet and the speed of light, that you can't drive a bullet that fast. So we know that's false. Also, the one true thing about it was the speed of light, 186,000 miles a second. That was true. This fable goes on, though, and says that the bear was not a big male grizzly bear. It was actually a mama bear. And the explorer had invaded the bear's territory. And so they had to play by the bear's rules. So the bear ate the explorer and recycled him into 3 cute little cubs. And the time when last time I told the story, the little cubs are out exploring on their own. Of course, that part wasn't true. But the one true part is the speed of light. And it's so hard to believe. You know, you could almost better believe than what else I told you. Now, I don't want this type of a fable to interfere with what I'm going to tell you, because everything here from here on is what the energy told me, and I want to demonstrate what you would find if you went out to a satellite dish and worked with it, or anywhere you're working with the electromagnetic energy, and it'll tell you the same thing it told me, and I want you to make up your mind. I want you to remember what you've learned in universities, colleges, but it won't always synchronize with what you've learned. The energy itself will tell you something different, and this is what I'm going to demonstrate. Now, once we realize that everything is measured in the speed of light, then if you sent something out 60 million times a second, that means in 1/60 millionth of a second it could travel 16 feet. We just measured that. So if you had a room 16 feet across and you had, say, mirrors on both walls, and you sent a beam of light across there, it would cross that room 60 million times in 1 second. That's pretty fast. So anyway, everything is measured from the speed of light. Now, you take the satellite signal. It's the 4 gigahertz frequency they're using, and also the 12 gigahertz frequency. And that gigahertz means, I would have said probably 4 billion cycles a second. Not million now, we're talking about billion cycles a second. I don't know if anybody can fathom what that really is, but that's fast. And the speed of, and the light itself vibrates at the rate of 600 trillion times a second. So we're getting a very short wavelengths when we get into light. But anyway, it's all based on the speed of light and the length of time it has to travel. Now, this is a satellite dish. It's a small one. It's actually with a solar reflector. But about 1984, I bought after doing a series of experimentations, I bought a solid metal dish because solid metal was the best reflector I could find. And it worked fine, except that they had painted it with a semi-gloss paint, and it was too smooth. And it so happened, I mean, there's a lot of happenstance here that took place that kind of pushed me into this. It seemed like it just led me into these problems, or if you want to call them problems, anyway, these discoveries. And one of the things happened was that the sun, along about the 4th of March, up in our area at least, gets behind the Clark belt. Now, how many of you people have a satellite dish? You have some hands out there? We don't have a lot we have 2 or 3 satellite dishes. Well, anyway, we'll describe satellite dishes a bit. But this is a feed horn. And a feed horn is nothing but a waveguide with a little antenna in there. And that little antenna looks just like a little button hook. And you pick up the horizontal wave, horizontal energy from a horizontal antenna, and you pick up a vertical energy from a vertical antenna. Now that one is laying a horizontal, you'd be picking up horizontal transmission. It wouldn't pick up vertical transmission because it's horizontal. This feed horn was in the focal point of this dish. I mean, this is a big 8-foot dish. And the sun got behind the Clark belt, which meant that the sun coming into the dish would focus on the feed horn, which has to be at the focal point. And I don't know why this happened, but they had sold me a PVC feed horn. I don't think you see them. I don't think you probably ever see any more of them. But it had a metal lining. It worked good. PVC won't hold the signal at all. The signal will go right through that big heavy block of PVC. It just don't disturb it. But the metal lining was a good liner for it. But the PVC feed horn couldn't handle the heat that come off of this here semi-gloss paint. And it just warped it. And I called the people where I got it. It was up in, well, we won't mention where it came from. And they said, I want to inform you that we're having a little problem here, and I'm not complaining, but I want you to be aware of this problem. And they said, well, it only happens twice a year. I said, hey, wait, but twice a year is too often to lose your equipment, you know. But I didn't tell them that. They said they wanted to see the feed horn, and they'd send me another one. So this is the other one I got. It's a metal feed horn. And it works good. Anyway, in order to stop the sunlight from destroying my equipment, I did quite a bit of experimenting to find out what would scatter the sunlight and what wouldn't disturb the satellite signal. So I took a piece of metal, something like this, it was a larger one. I laid it out in the morning in the sun and let the sun hit this painted squares of this metal. And it so happens that this here particular green that I used here was a flat latex, same as colors our house. But on a real grazing angle of the sun, you're looking at the shadowy sides of all these little grains of paint, and it looked black. It actually looked almost black, like a shadow. You look down on it, it would look green. You look at it from the front side, it would look green. But from the shadow side, it looked black. And so I used that to paint the dish with. That worked fine. And but really before that, I had another thing that happened that was really a part of the whole process. I bought a screen dish, and the screen dish had pedals on it. Now, pedals would be sections like this here on the satellite dish. And I thought, well, maybe somebody along the line hadn't really figured everything out just right, and I was going to change these pedals on the dish to see if I could get a better reflecting surface. I had no idea what the best reflecting surface would be. I really assumed that maybe 2-inch chicken wire, which had some kind of relation to the size of the satellite signal, might be a better reflecting surface. That turned out to be an error. It wasn't that way at all. But anyway, this the screen dish had a problem with it. This is a feed horn, and this is not the low noise converter that I had on there. Actually, I had a low noise converter. This is a low noise amplifier, and it goes on this way or it goes on this way. And this little 90-degree bend on there was put on because I wanted to put a weather cap over the feed horn to keep it from getting rain and things into the feed horn. And I did a lot of experimenting because my signal was real poor. And I'd been in the television business for 14 years. I got into it after doing experimenting with antennas and doing building antennas, doing a lot of antenna work, especially out in the country. I used a lot of rhombic type antennas, which is a long wire antenna that goes out in a big diamond shape, 200 feet usually long. And they were real strong, about twice as strong as your best Yagis you could get. And a Yagi cut for one channel. Now you get these combination antennas that are taking on lots of different frequencies. They won't do the job that a single antenna cut for one frequency will do. And we had only one channel then out of Eureka that I was working with. So it worked out pretty good because they took off 3 of the major networks, and there was no discussion in the house of what you listened to. You either watched television or you didn't, and you got what you had. And it really amazed me that later on that people would actually spend a lot of money to get to maybe 40 or 50 channels because you can't watch too many at a time. And they were doing the picking for us. We didn't have to search through and pick what we wanted. Anyway, people did go for a lot of channels, and I guess I grew up in the country and always worked in kind of a low scale of income, and I didn't mind that. I was happy to do that, but I didn't feel that people should be spending $50 a month for a television when they could get all they wanted for one antenna and maybe it'd last for 5 years. And so anyway, that's kind of giving you my background of my thinking, see. Anyway, I was going to say that I did a lot of experimenting, and I found that this there bend in the waveguide is what that actually is, was causing trouble. When I took that off of there, everything worked fine. But before that, I developed little probe antennas I could hook in on the thing, and it improved my signal. Then I tried putting a lens over the entrance and to see out on the dish farther, and it also worked. But the two things were so different that I said, hey, something's wrong. So I took the feed horn right out of the focal point. I took the low noise converter, not this one, but one not something similar to it, held it right in the focal point, and I could get the signal, you know. I could turn it horizontally and get the horizontal signal. I could turn it vertically and get the vertical signal. Now, how many, well, I shouldn't ask questions, I guess. They send out from the satellite, they send out vertically polarized signal and horizontally polarized signal. And they do this with radio and with a ham radio. Most of the antennas are vertical, so it just sends out a vertically polarized signal. And the one don't interrupt the other at all, so they can send out 12 channels off of one transponder, or 12 transponders off of one satellite in one, vertically, and one 12 horizontally. That gives them 24 channels on one satellite. And they got a lot of satellites up there too. Now, these satellites are all in the geosynchronous orbit over the equator. They have to be right over the equator to stay in one point over the Earth. They couldn't be at some other point because then they'd be going some other direction like that. So it'd be in one point right over the equator, and that is around 22,300 miles above the equator. Well, that's about 3 times the diameter of the Earth out there in space, away from the Earth. And so we're like a hub of a whole wagon wheel, and they're out on the rim. And they are in that position for a purpose that that is where the balance between centrifugal force and centripetal force would remain in that one orbit. I stopped myself when I said centrifugal force because I started realizing later on there's no such a thing as centrifugal force. I can explain that, but maybe I should get into that later. Well, I will explain it a little bit right now. Newton's law of mass and motion says that a thing is put into motion that continues in a straight line and at constant speed until it's changed by some other outside force. Well, centrifugal force, what is actually happening is, say for instance you had a string on a rock and we string it around like that. That rock wants to take off in a straight line, but that string is holding it from that line. So we have mass and motion trying to keep things in a straight line, and the centripetal force pulling it down to the center. And there's no actual such a thing as centrifugal force. We say centrifugal force because everything wants to fly right away from the center if we let it go. But actually it wants to go in a straight line. The moon would do that too. They say the moon falls toward the Earth at such a rate as it goes around the Earth. Well, to me, if it falls toward the Earth, it would get closer. But what it is falling out of a straight line trajectory toward the Earth, and it pulls it into this orbit. And so it goes around. And it's falling because that's what gravity is all about. Things are falling toward the Earth. They're being pulled toward the Earth by gravity. Anyway, in order to get the problem out of my dish, I painted it with this latex paint. And here again, I was writing up all my experiments, and I had a whole bunch of papers or things. And I was out, and then 6 months went by, I guess, after I painted the dish, and I was out leaning against the dish and looking at it and says, how come that's scattering the sunlight and it's not bothering the TV signal? And I wondered if you put it on the screen there, would that help any? You might try. Well, not really. Yeah, it might, because I'm going to do some experimenting here, and you can see a lot better. So I got to looking at that, and I said, well, of course, it's the grains of the paint that's doing it. They're scattering the photons of light. But the thing is that it wasn't bothering the TV signal, and the laws of reflection are that the angle of incidence is equal to the angle of reflection. But when a signal comes into a dish like this, this would be, if it come in like that, it would go out like that if it was in one plane, a plane wave. But this has to be prepared to bounce to this center, no matter how that comes in there. I mean, coming straight in now. And why I have the dish setting this way is so that I can, its gravity will pull anything straight into the dish. But it has to be in such a shape that it's prepared to go to the focal point every time. If I was to go this way, I could do it, or if I was to go this way, I could do it. But I'm not prepared to go this way to the focal point from the descriptions of reflection. So I figured that the only thing that can do that is a sphere. It has to be equal in all dimensions. If I twist my hand around, I come up with a sphere. So it has to be equal in all dimensions. So I figured that the units of energy composing the wavefront, now it comes from a point source. It's shot out in all directions like a 4th of July rocket, you know, up there, it explodes in the air and it goes out in all directions. It don't go too much toward the ends of the antenna. It goes mostly straight forward, but it goes all the way around the antenna. And so that's energy I'm talking about now, transmission of TV signal or whatever. And they're all the same. I mean, the sun, all these are just a different frequency. So if there's an inverse square law that governs the spreading of light. And if light spread sideways, it'd just be by the simple distance that it would weaken. But it actually goes up this way too, you see. So you got the third dimension of it. So it thins and gets further apart by the inverse square law. And so if you had a light and say I was 2 feet from that light and have a certain level, if I went 2 more feet, I'd have only 1/4 of the level I would at the first level. Now, going back to the spherical shape, if I was to drop a ball in this dish, it should hit that focal point, no matter where it hits the dish. No matter how close I am to the focal point, it should hit that, how close I am to the center, it should hit that focal point. And it'll do it. There's no other shape that'll do that. It's almost absolutely conclusive that the units of energy composing the energy front, now I'm not going to use wave anymore because I think this will destroy the wave theory and go totally to the photon theory. And it just has to be spherical units of energy. Now, if it's a sphere, it has to have a size to it. Now we're talking about third dimension. We aren't talking about a plane anymore. It has to have a third dimension. So how big would those units of energy be? Well, I had no idea what I was going to come up with on this one, but in my experimentation, you want to come up and help me a bit, please? In my experimentation, I had tested all different kinds of screens and wires and things, and just a minute. Well, I was changing the pedals or trying to, but that was a big job. That didn't work out at all. So I put the screen in front of the feed horn and let the signal come through the screens, and I could do just as good that way. And it was a real simple test, and anybody with your satellite dish can do this. It should work the same way anytime you try it, because if the things are a true experiment, it's going to work every time. And so I was able to find that the satellite signal, we'll hold it up a little higher. Is this showing on the dish over there?
Yes.
If I drop this through there, it'll hit the focal point. No matter where I hit it, it'll do that. Okay, so we know that the satellite signal will go through 2-inch chicken wire. Now, oh, we have one other thing with this here. This is going to sound kind of basic and maybe almost stupid in a way, but you can see light goes through there too. In other words, photons of light go through and the satellite signal goes through. Let's get a little larger unit of energy. Here is one, here, I need that yet. This is a unit of energy then, if we're saying that it does have dimension, and it is related to the wavelength. And now I'm using wavelength now as a measurement. And this is about the size of the energy coming off of UHF channel 27. Now, it won't go through there, obviously. This makes a good reflector for it, actually. It won't go through. But the satellite signal will go through and light will go through. Okay, we got doing a little rough dimensions here. Now, if I take the screen, regular window screen, about 1/16 of an inch mesh, and I drop a satellite signal onto it, it just bounces. It makes a good reflecting surface for satellite signal. Yet you can see through it, light goes through it. If you can see the glare up here on the screen, you probably can see that from the light. That is telling you that those screens in there are large enough to make a bounce surface for the photons of light. If you recognize then that, oh, well, wait a bit. Going back to my screen work, I determined from the needle readings and whatnot that it had to be the half wavelength. In other words, the units of energy composing the wavefront had to be the half wavelength in diameter. And so if you recognize that, then the photons of light at about 50 thousandths of an inch on the wavelength would be about 100 thousandths of an inch. This is the mid-range of white light now. Would have to be about 100 thousandths of an inch. So those screens then are, I mean the screen itself, the wires, are large enough to make a bounce surface. They have to then be over 100 thousandths of an inch in size. When you start getting into all this type of thing, you will start looking at the clouds and you'll see, hey, those clouds, the little driplets of moisture are large enough. They have to be over 100 thousandths of an inch in size to make a bounce surface for white light. Physicists will probably tell you, some of them will I know, that the atmosphere absorbs and re-radiates energy as it comes through it. But that's not true, because if it was absorbed and re-radiated, unless that air was white hot, it would come out in some other frequency. If it goes into the earth and heats the earth, it radiates out in some other frequency, like infrared or some other lower frequency. But they're all electromagnetic energy. Anyway, let's get a little perspective on size here. This is a 1/16 of an inch. That means 100 thousandths of an inch in each little unit. 6,000 of them could go through one hole in this screen side by side without even being inside each other, and there's no problem with them being inside each other as far as I know. 6,000 sideways and 6,000 layers of them would mean 36 million photons of light could go through one hole of the screen at one time. And if they're traveling at 186,000 miles a second, that means a string of them 7 times around the Earth could pass through that hole in that screen in 1 second. That's why we see. That's why we're able to see things. All this energy is coming at us from all directions. And the only thing we see is what goes through our eyes and is impressed on the rods and cones and the retina of our eye. And they say there's 135 million rods and cones, or maybe that's the rods and not the cones. But anyway, there's a lot of receptors in there. And they all work just like that antenna. But they're very small, and they're the right size to take the energy out of a photon of light. And if you think about the speed with which those little photons are traveling, and 36 million could go through a hole side by side without just touching each other, then you realize that photons of light are almost as thick as molecules in the air. There have to be a lot of them. And especially, they travel so fast that they could repeat themselves, you know. A molecule stands in one position, or maybe it rises because of expansion, but these things are going, and they're always going. They never stop. They'll keep going and keep energizing things, heating, whatever you want to call it, until the whole universe is uniform in heat. You talk about perpetual motion. They say there's no such a thing as perpetual motion, but they're put with the Hubble telescope up. They're expecting to see photons of energy traveling for millions of years, and it does take time. There's a time lapse on it, and so it takes time, and they can see back into history that way, maybe millions of years, because these energies are bringing what they left from, what they bounced off of. They're bringing the information to us millions of years later, and so it's perpetual motion as far as I'm concerned. You get several million years, that's perpetual. It's beyond perpetual for me. Anyway, I think the problem with perpetual motion is people try to get more energy out than they put in. And I think that's where perpetual motion has a problem. Okay, we just determined the shape, and we get some measurement of size. In the past, they used to, with like Channel 3 of, not to say Eureka, TV Channel 3, they used to put up a screen, billboard-like things, to reflect the signal down into a valley that couldn't get it straight in over the hills, because it travels relatively straight. In fact, I should say it travels in a straight line. I don't see any deviation except by a lot of other things that interrupt it, like surfaces and diffraction and refraction and scattering and all that. But anyway, they put up these big billboards of chicken wire, and I always used to wonder, I was in the television business for 14 years. Did I mention that? Anyway, I always wondered why they used chicken wire. But you take a unit of energy then of channel 3 would be about 8 feet in diameter. And it would be a good bounce surface for 2-inch chicken wire. You'd probably lose maybe 5–10% going through. The rest of it would all be reflected back. There's another thought that just came up. If this energy can be divided and divided down to nothingness, I guess, but one of the steps when I was working with this here was that I used, I went from 2-inch chicken wire, go right through it. 1-inch chicken wire, I'd lose about 1/3 of my signal. I went down to 1/2-inch hardware cloth, and I'd lose about 2/3 of my signal. Right on down to solid metal, where I just lost everything. Actually, the screen, I was just showing you, it didn't get through the screen either. So it can be divided, energy. Now, everything was going fine. And I decided that, hey, I'm retired. This is 83, 84. I'm retired, I got lots of time, and my wife was taking care of an elderly aunt, and she was kind of pinned down at the house, and I stayed around to help, and it was all part of the things that caused all this to happen. When I'd taken this low noise converter, this is a low noise amplifier, I could get the vertical signal and the horizontal signal. And I thought, well, why don't I just make a little slot across the front of a feed horn, and I can isolate the vertical and horizontal signal. Can you all see that? Just a soup can with a half-inch slice in it. And so, yeah, it worked. I get about 75% of the signal through this, of the vertical signal, and the horizontal signal wouldn't go through at all. So I was then writing up my experiments, like I always do, and I said, well, the vertical signal is going through the vertical slot, and the horizontal signal is going through the horizontal slot. And I thought, hey, I didn't look at the antenna in there. I better go back and check that. I had to set my experiment up. But again, I'm retired. I had to be doing something. So keep myself thinking. So I looked in there, and so help me, the antenna was horizontal, was going through the vertical slot. So I picked up a good physics book, and I think all of them will say the same thing, probably yet today. And it says the vertically polarized signal goes through a vertical slot, and the horizontal goes through the horizontal slot. But that's 90 degrees out of what it actually is. So I thought, well, God, I wonder how many other things they missed. You know, this is this is interesting. So, but I had to kind of scratch my head a little bit on this one because I didn't understand it right away. And then I read in Harvey E. White's classical modern physics. I was reading about Hans Christian Ørsted's right-hand rule. And that's a real simple rule and a very valid rule. And if you take a conductor and, well, actually, if you have a magnetic field, I don't know if I have a magnetic field drawn here. I'm going to have to just describe that because I haven't got time to do the drawing. If I had two magnets, one above the other here, I have north, south, and here's a magnetic field between those two. You want to hold your hands up here with these? Make a couple of magnets here. Okay. Now, here we got a field, a magnetic field going between, and it's traveling one direction through that. If I was to put this conductor in there, nothing in the world is going to happen. If I was to run it up and down with the lines of force, nothing's going to happen. But I run it across the lines of force, and it's going to create a current in this wire. If I run it the opposite way, the current's going to run the opposite way. And if I put the rod in the field, and then I run a current through it, that current is going to create a field around it. And when it does, it's going to be, this is all going one direction, this goes clear around, so it's going to kick it right out of that field. And that's basically the principle of the electric motor. And if I push it through the field, that's the principle of the generator. I'm generating current. But it has to be movement. You can't generate anything when everything's standing still. So I think we're through with your hands there. You want to have them back? So anyway, Ørsted says that if you run a current in a wire, a field will form around it. And that's called the right-hand rule. Now, probably a lot of you people have heard of the right-hand rule. But the problem with the right and the left-hand rule is that back in those days, they didn't know which way the current run. And they thought it moved from positive to negative, and maybe you could still say that. In fact, that's a conventional way of thinking of it. But it actually it's electrons that move because they're so much lighter. And so I avoided all that by just saying that if you put your hand around a wire, the compass will point across that wire if you got a current. Now you got a DC current in here, a direct current, and hooked to a battery here. Your thumb will point at the negative terminal of the battery, in other words, the source of the electrons. If you reverse it, it'd have to be this way. So you get an alternating current going back and forth, and you get fields that form first this way, and then you form this way and this way. And they're forming one inside the other, so they can't really collapse. They're driven off, and they drive off, and that's when you get transmission. And so it's driving off fields one way and then the other, like that. So it's not necessarily positive and negative, but it's one way up and the other way up. And if you have a current field crossing a conductor, now it has to cut the lines of force. If I go this way, they go right through. It don't do anything. For instance, if I had this is a rod about the right length for channel 27 UHF. If I go this way, nothing happens at all. It goes right through. If I go this way, nothing much will happen because I am cutting the lines of force, but they're balanced on each side this way. If I go this way through it, it just goes right through. Nothing happens. But if I cut the lines of force of these transmitted units of energy, you take the maximum signal, maximum energy out of it, And when it does take the energy out, it creates a current in the wire. And that current, when it runs, forms a field that opposes the one that formed it. In other words, that's Lenz's law, and it seems to be a very valid law. So if you turn it at a 45, you get part of the signal out. You get 0, 40, 45 would be about half, and across it we get the full amount of signal out of there. So I was able, I have a reel of wire somewhere. Here we are. It's the same thing would happen. Now I am at this time not using a satellite dish. I'm using a UHF transmitter and a little dipole antenna, just a little thing about, well, just about this long. And if I was to hold it up, well, let's just hold it up this way here. If I was to hold this up this way, that signal would go right through, and it would go right onto my antenna. If I was to hold it crossways, it would bounce the signal right back. It's not absorbing the signal. It's bouncing it back off of there. Now, with polarizing films, somebody will say, well, it absorbs the signal one way and it goes through the other way. But you can test it very easily in this large dimensions. You can know that it is reflecting it back off of there. It's just bouncing back. And all of energy travels in a bounce now. It's not a surface contact like that and taking off. It actually, the trajectory of energy come down like a ball and start up here. You see that this surface of the ball hit, but this is where the trajectory of that energy is. And I don't think in a lot of engineering they even take that into consideration yet, because they don't recognize spherical shapes. And they're going to have to, as far as I can see. But I don't want to make up your minds. I want you to see what this energy has taught me, and then you can decide for yourself. So this, anyway, we are now polarizing units of energy through a grill, same as polarizing film will do it for light. So, yeah, I think we're through that. So we're determining now the magnetic structure of a unit of energy. And they say, hey, you can't do that. I mean, but I don't like the word can't. I think things are difficult. Yeah, I'll agree with that. But can't as a... Well, let's go back a little farther. I used to say, hey, they can't go through space. There's nothing to push on. What are you going to push on to get through space, you know? There's nothing out there. Well, I had to change my opinion a lot of that. There's nothing out there. Not much there isn't. There's a solid mass of units of energy coming from the sun. The only reason we believe there's nothing out there because energy does not require a space of its own. Molecules require a space. They're like cars. You try to put two cars in the same spot, you know, you're going to have a crash, and you better be insured. And molecules are like that. Cars are made up of molecules. But energy does not require a space of its own. It can go right through itself. It can go through all other energies, and it appears to be empty because it's just loaded with energy. Oh, sure, we have moons and asteroids and debris and broken down satellites and things out there, but you know, basically space, they say, is empty. Now, I probably will jump around a little bit on this and get lost here, but there's lots of other ways of telling the size of units of energy. If I was to, there's a piece of sandpaper, just a plain sandpaper. These little grains of sand are very glossy. Each little grain is. So if I was to slam a bunch of light down on there at 186,000 miles a second, it would just scatter in all directions. But if I was to put that same light down on a mirror, it would bounce all together and it would be in the same relative position. If I was coming off of a slanting surface, now this was a mirror here, I come out there and all the little photons of light hit like that and come up to your eye, they would all be in the same position, and you'd be seeing, say, the sun back here, if this was the sun that was creating that light. And there's no reversing of this energy at a mirror. I used to think it reversed itself somehow. In fact, I had a physicist tell me not too long ago that something about it has to be a metal surface to create a reflection, because if the metal has to form a field that rejects the field that is approaching it. But that's not true. You can have a field, you can have glass. Light will bounce off of glass. It's the smoothness of the surface that's critical. If you have a perfectly smooth pond of water, that light will come down and bounce right off it. If you have a rough surface, it'll scatter it because it hits in different angles and goes off in different directions. That's the same with the satellite signal. But with UHF, not UHF, it's VHF channel 3, units of energy 8 feet in diameter, I've done a lot of testing with test dipoles like that on a long pole, and it'll bounce off of a very rough ground, actually. You know, there can be boulders like that, and still you can go up on an altitude and you get a maximum reading from the signal that comes off of the ground on a bounce and the signal that's coming straight in don't bounce. And as you synchronize those points, you'll find a maximum reading. As you go higher, you'll get a null reading, the same as I did when I was moving my antenna back and forth. You get a null reading or a lower reading, and you go up higher and you get another maximum. And so they always used to say you got to check for the height of your antenna to put it the right height. And that's simply to synchronize with the bounce wave. But each wave being of different, did I say wave? Bouncing energy. Each energy has a different size, and so the smoothness of the ground has to be relative to the energy. Because if I was trying to receive satellite signal on gravel, it wouldn't bounce off. It would just scatter it because it's so small. It's about the size of this little. Well, actually, satellite signal is the size of a ping pong ball. That's an inch and a half in diameter. That's exactly what it is. So we have many ways to measure units of energy. We can measure their bounce characteristics. And we can measure, like I say, screening them through gravel. Pardon me, screening them like gravel through wire. Now, energy has another characteristic that kind of surprised me. Here I have a sheet of metal, good reflector. If I had a little UHF antenna out there, I have one somewhere around here, a little UHF antenna out at a focal point, and I would send signal back to it. In fact, a smaller, this makes a good reflecting surface for UHF. It's large enough to make a reflecting surface. It makes a good reflecting surface. But if I was to get a larger reflecting surface, and I'm having an antenna now out here in front, and I'm reflecting it back to this antenna. If I was to get a larger surface, I could increase that by bending it so that it brought everything into the focal point from the sides. If I wanted to get it from the top and bottom, I'd bend it the other way. And what I'm doing actually is making a parabolic dish. So getting everything to come into the focal point. So I have a chart here that I can explain parabolic dishes, but I'll do that a little later if we have time even. Now, here's a fiberglass. It goes right through it. 10 more minutes? 5. Okay.
I know you could go on for a couple hours.
Oh, I could go on all day if you want me to. Maybe these people wouldn't mind, I don't know. Anyway, this is fiberglass to go right through it. Now here's something painted with aluminum paint. It goes right through it. The reason for that is that that's not a solid sheet of metal, and there's just a whole lot of little flecks of aluminum paint that it'd be then transparent. That is transparent to satellite signal, to UHF. So then if you go a little farther with it, you can put a lot of squares like that. And that's transparent to UHF too, because there's little small squares. Now, somewhere I have these cups. You find them? What? Oh, well, I better not get into that. I don't have time for it. Well, here they are right in front of me. You can do your experimenting right at your satellite dish, a whole lot of it. I was interested in knowing what raindrops would do to satellite. Here I cut a lot of raindrops. They're made of little aluminum squares, and just, you know, I use expensive equipment here. Jam it in the entrance of a feed horn, and you can tell the signal will go right through it. Okay, now if I enlarge that to 1.5 inches, it just kicks all the signal back out. It won't go through that. If I take a grill of wires, same as as the grill I had here, but for satellite signal. Put that in there, it'll separate the vertical from the horizontal signal. So it always works the same no matter what size you have. It's all the same material. And then this would be transparent to satellite signal, while photons of light, you can see it reflecting. They're hitting those little surfaces, reflecting off. The 12 gigahertz frequency, which is only a ½ inch in diameter, would probably bounce off of all these little squares. But this will go right through it. So we have a kind of a high and a low. In other words, if it's too small a piece, it just goes right through the energy. Now, the energy is traveling, 186,000 miles a second. So when I say it goes through it, I mean the energy is just passing around it. Yes. One of the basic things I'm trying to do here is to make it so simple. I shouldn't have put it that way. I just reduce it to simplicity so that the average person can recognize what's happening. And this energy has been telling me this. This don't come out of books. You won't find this in books. In fact, the matter, you'll only find it in my books. And okay, let's ask you a question. Do you have any questions that seem to come to mind? We got one back there. In fact, there's two of them. We get the first gentleman.
There's a lot of experimenters like Keeley and Tesla that use large circular globes as antennas. What were they doing and why is that?
Antennas are rather a field of their own. You take a dipole antenna like that, and I probably won't answer your question even. You take a dipole antenna like that, quarter wave, it should be right square across the wave. If you increase that, you got to pick up the signal more and more this way. If you get out 6 wavelengths, you only have a 20-degree angle between straight. And so the longer the antenna, the more it has to be faced at the wave, at the source of the energy. And if you get out so far and as best you can do, then you could come back this way and you can add, these will add together, more like a sailboat tacking, you know. And they'll add together and make a strong signal at this end. But it all has to feed in at the right, in the right phase. I don't think that answers your question at all. There's a gentleman way back there.
Yes, I'd like to know, pardon me, why your PVC feed horn melted. What is your explanation?
I didn't get that.
Why?
Oh, why the PVC melted at the feed horn? The sun got behind the Clark belt, and the dish, being painted with glossy paint, probably developed maybe 600-700 degrees up there, and it got very hot, just actually from heat. But heat again is one of the electromagnetic energies. Huh? Oh, who had that?
What's the Clark belt?
The Clark belt. I think this was some fellow by the name of Clark was in comics or something, but he determined that it could be something put in geosynchronous orbit, and they eventually found that was true. And so it's the belt around the equator, 22,300 miles above the equator, where they put all these geosynchronous satellites, and they're traveling at a certain speed, but the Earth is rotating at the same speed, so they remain over that point. And so you point your satellite dish right at them. I see a hand back over here.
Yes, in reference to your comment about the diameter of the sphere,
Yes.
Keeley is my specialty, and he, as well as modern science, say that oscillations occur across the diameter of a structure. So you're exactly right on that. We've long since known that, or we believe, the people who are into Keeley think that oscillations do occur in spherical packets. But that's a fact that's just been proven in science about 30 years ago, that oscillations do occur across the mass, across the diameter, so that's true. So.
Yeah, I'd like to visit with you a little bit more on that, but I'm glad you're saying that it coincides. That. Yeah, sure. Okay. Well, we'll just start moving these things from here then.
Yeah, sorry to cut Larry off because I know he's got really important things, and I would invite everybody interested to speak with him. He's written 3 books so far, self-published: My Electromagnetic Spherical Theory and My Experiments to Prove It, Electromagnetic Heat, and the Electromagnetic Sea in Which We Live. Now, like I say, those of you who have seen our laboratory videos that recognize these